Okay, this is from January 7th. I thought it was cool though, so. Anyway, multi-wavelength view of a supernova remnant. Includes data from ESA's Herschel Space Observatory. Shows the remnants of an explosion, not of the colorful type, ignited during celebrations, but of the stellar kind. In the image dubbed G54.1 plus 0.3 is a supernova remnant, leftovers of a massive star that died a violent death. It's located 20,000 light years away from us in the northern constellation of Sagitta, I guess. The Arrow. Y'all know how that goes. I'm not even going to read all that, but I just wanted to share that. I thought it was really cool. So check it out. Anyway, and here is this. I thought this was pretty interesting too. I don't know much about it, but anyway. Laser blasted plasma is colder than deep space, literally. Researchers who make the coldest plasmas in the universe just found a way to make them even colder by blasting them with lasers. They cooled the plasma to around 50 thousandths of a degree above absolute zero, about 50 times colder than in deep space. It could reveal how similar plasmas behave at the centers of white dwarf stars and deep in the core of gas planets like Jupiter. And there, see what plasma is. Temperatures of naturally occurring plasma are typically very high. Plasma on the surface of the sun is 10,800 degrees Fahrenheit. By cooling plasma, scientists can make more detailed observations in order to better understand its behavior under extreme conditions. So why use lasers? They say, they asking. The laser cooling takes advantage of the fact that light has momentum. This guy says, if I have an ion in the plasma and I have a laser beam scattering light off that ion, every time that ion scatters a photon, it gets a push in the direction of the laser beam. This means that if a laser beam opposes the ion's natural motion, every time the ion scatters light, it loses some momentum, which slows it down. It's like walking uphill or in molasses, he said. For their experiments, he and his colleagues produced small amounts of neutral plasma with a relatively equal number of positive and negative charges, vaporizing strontium metal and then ionizing the cloud. The plasma dissipated in less than 100 millionths of a second, which didn't leave the scientists much time to cool it down before it disappeared. For the laser cooling to work, they need to pre-cool the plasma, slowing the ions down even more. In the end, the resulting plasma was about 4 times colder than any that had ever been created before. So, it took about assembling the pieces needed to generate highly cooled plasma took about 20 years, though the experiment themselves lasted less than a fraction of a second. That's really fascinating stuff there. If you want to check it out, read some more about it there, I'll put the links there below for this. And this I thought was really neat too. So, what a tiny electron reveals about the structure of the universe. And their electron is commonly known as one of the main components of atoms, making the world around us. And it's telling you what you've learned about in school is false. It's far from the truth. It says, it is the electrons surrounding the nucleus of every atom that determine how chemical reactions proceed. Their uses in industry are abundant, from electronics and welding to imaging and advanced particle accelerators. Recently, however, a physics experiment called Advanced Cold Molecular Electron put an electron on the center stage of scientific inquiry. The question that the collaboration tried to address was, what is the shape of an electron? Anyway, I'll leave this below. So, anyway, see you later.